In the previous session, we spoke about how the stack frame uh, looks for interrupts without floating point unit active. But we did not, though we saw the registers being saved onto the stack, we did not see the registers being restored from the stack into the register values, because the register values did not change, so we did not see the register values being restored. So what we'll do in this session, this demo, is to also verify if the register values are restored or not. So we will run the same code, and when we get into the ISR, what we'll do is we'll change the register values, and if the registers are restored by the Cortex M4 core, then we will see that once we are back into the main function, the old register values are going to be populated. So let us put the program in debug first and proceed from there. So the program has gone into debug mode. So let's do the same set of steps that we had been doing, but let us continue here. And now we have hit line 33 as we did previously. What we'll do now is we'll make a note of all the registers that are actually saved onto the stack. So we have register R0, R1, R2, R3. Okay. Now what you see here and what will actually be saved onto the stack will be slightly different, because once it is now in this instruction, and suppose this instruction is executed and then the interrupt occurs between here and here, the while loop, certain registers might be getting used which might not be captured here. So what we'll do is we will run the code and we will let it hit the breakpoint. Once it hits the breakpoint, that is the ISR breakpoint, we will make a note of all the register values that we have saved in the stack. Once that's done, and then we will change the register values in the here while it is still stuck in the ISR, and then we'll return from the interrupt, and then we will check if the old register values that were on the stack has been restored or not. So these are the steps that we are going to take. So like before, let us check what the stack pointer value is now here. Okay, so like previous, because the code has not been changed, it is 0x20002B8C. Now this value will be different in your case if you write another program, but the logic is the same. For example, you have the stack pointer value, and whatever new stack pointer value you get, you subtract and get the size of the stack, and then you do your checks. So let's continue and we'll hit the ISR hopefully. So we have come into the ISR. Now let's check the stack pointer again. It is 2B64. Now in the previous case we have seen when it becomes 2B64, and that is when a function call from the interrupt handler is commented out. So basically what happens is, if you see, the push and the pop is for only one, that is a stack pointer value. It is the push and pop of the stack pointer value for the handler, and that is the reason we see that the stack pointer is one less than the previous case. So right now the stack pointer, so we'll just calculate mentally because we've seen this before. So previously, if it is 11 words, now it is going to be 10 words. So we know what the stack pointer is currently. We'll just check for 10 words. And because if you subtract, do it yourself. If you subtract this value, the old stack pointer that you see and the new stack pointer that you see here, you'll see that the value will be 40 decimal, and 40 decimal will be 10 words. So now let's print the stack and see what we have. So x, so right now we have 10 items, so we'll do 10x and then $sp. So now this is the value that has been pushed. Okay, so R0, R1, R2, R3, all these values start from here. So all our complete stack contents. Now let us look at the stack content from another place now. It's pretty much the same. So we have R0, R1, R2, R3, R12, LR, PC, and XPSR. So there is a double word alignment that happens. Here it is not happening. So this is just a double word alignment that the hardware does for the stacks if the stacks are not double word aligned. So now let's get back to the code. So we have R0, R1, R2, R3, R12, LR, PC, and XPSR. So let us write down the values once again as we did, or okay, let us leave it because we'll have to scroll up and those values are going to clutter the area here. But R0, R1, R2, R3, R12, PC, LR, XPSR. Now so we will have to keep these values in mind. So what we'll do now is we'll change the values of the general registers here. So it is as if we are in the sysdig handler and we'll change the values of the general registers. So we'll only alter R0, R1, R2, R3, but then we can, since this will remain, these values will remain, we can, once we are out of the interrupt, we will compare these values with the registers once the values are supposed to be restored. So let us put some other value here. For example, let's put 0x34, any random value which is different from what is currently there. So 0xff, 0x77, and 0x AB, suppose. So these registers are having different values now from what they had before jumping to this ISR. Now what we'll do now is we'll go back to the main and we'll set a breakpoint in while as we did previously, and we'll come out of the interrupt. So now the values are changed for these registers, and so we have a different 2b64. So if you see, the stack pointer value is different, 2b64. LR is of course FFF9. This could have been different if this toggle LED was actually uncommented. Okay, so here the LR is as it is, but the LR could change. We saw this before. The PC is different, program counter is different, 4E4. Okay, so that is the current program counter, and then you have the XPSR value as this. So now let's come out of the interrupt and try to see what has happened to these values again. So now let us do a continue and just hope that it hits the breakpoint in while. So it has hit the breakpoint here. Now we see that some values have changed here. We'll not bother about R7 because R7 is not saved on the stack anyway, so we are not concerned about R7 here. We will only check those values which we had left, which we had left while leaving this main function. So those values should be restored from the stack to here. So let's see. 20022760 was the R0 value. So we see that the R0 has been restored here. All zeros and 6 restored. R2 all zeros restored. So R2 had a different value which we deliberately put here. R3 41B 3712 restored. Okay. Now let's see what happened to the R1, R0, R1, R2, R3. Okay. R12. So R12 is 0. So we didn't change the R12 value, but it is restored. And then we have your LR, PC and XPSR. So what is the LR value now? 80001D1. So this was the LR value previously before jumping from the function. Have a look at this. So it has been restored. Okay. PC was 80001D8. So just check the PC value. Sometimes this value may not always be, this value could be one memory location ahead, or it could be this. Okay, it depends on where the interrupt exactly occurred. So here it is now 8001D8 because this was interrupted at this point. Okay, and then LR, you have link register, LR PC, then you have XPSR. So XPSR value has changed. Okay, so from what we see here, so thus we see that most of the stack values have been restored. XPSR has changed because there must have been some situations, that is when we came back from the ISR and we hit this breakpoint, it may have changed within that time. But as you can see, most of the values are restored to the registers and the stack pointer, link register, program counter, so on and so forth. So that is what happens. So now we see that the restoration of the values are also done properly.